And thank you so much for the invitation and yeah, I've been really enjoying the talks. So I'm excited to give a talk, but more importantly, to see all the wonderful talks that I've gotten to hear. So I will tell you about which Schubert varieties are Hessenberg varieties, and this is joint work with my colleagues here at WashU, Martha Prikop and John Sharesh. And so I'll start. So yeah, we heard about the flag variety yesterday, but I wanna maybe just repeat it. So the flag variety is just sequences of vector spaces in C to the n that satisfy this ascending condition, right? So it's strictly ascending sequences of vector spaces in C to the n. But this variety, one of the features that makes it have a lot of structure is that you can describe it as G mod B, where G is the special linear group and B consists of the upper triangular matrices. So we can have two perspectives on elements of the flag variety. One is the flag descriptions as sequences of vector spaces, but then the other one is as cosets. And this coset description, like we will exploit that structure like almost immediately to define what Schubert varieties are. So in particular, we get an action of this subgroup on the flag variety that, like, one can of course describe it on the flags, but it's very immediate from the description as G mod B. It's just the action of a B with your coset. You just multiply B with your matrix representing your coset, and that is what this action is. So using this action, we can construct Schubert varieties. So if you start with a permutation in Sn, let me denote by, well, I'll put a dot on top just to distinguish it, but I'm gonna let this be the following flag. So it's the flag where you just list your standard basis vectors in the order determined by your permutation. And so that is indeed a flag. It's strictly ascending sequence of vector subspaces of C to the n. And if you go ahead and take this action, act on this point by B, so look at this orbit, and then you close it, you end up with a Schubert variety. And so Schubert varieties, well, they are combinatorial varieties that are very nice to study because you have this nice interaction between the combinatorics of your permutation and the geometry. And then there's like a third branch of tools you can use to study Schubert varieties or subvarieties of the flag variety, which is representation theory. And I will touch that very little towards the end. And so let me give you, okay, so this is like a group theoretic description, but as I said, there's like these 2 points of view on flags. So there is a flag description of Schubert varieties that it's very combinatorial. So if you want to characterize which flags are in a Schubert variety, you can define the following combinatorial number. So for each pair of numbers in n, so p and q less than or equal to n integers, then you can define this number to be the number of integers less than or equal to p, such that w sub I is less than or equal to q. And if you construct this number, you can characterize the flags in your Schubert variety as those such that for all pair of p and q's, this dimension is at least this combinatorial number. And this combinatorial number, it did appear yesterday in Colleen's talk, so you can describe it in terms of Rothe diagrams or rank matrices. So this is very combinatorial. So your takeaway for Schubert varieties, in case you haven't seen them, is, well, you basically have Schubert varieties that, and you have flags and sequences of vector spaces that satisfy this combinatorial condition. And so, as I was saying before, we have this dictionary between combinatorics and geometry for Schubert varieties. And so here is, okay, so some properties of this variety. First, they are irreducible. So we will see other varieties today that are not necessarily irreducible, but Schubert varieties always are, and they're being invariant. So because of this definition, the way we define them here, the Borel acts on this Schubert variety and it fixes, as I said, the Schubert variety. Now, combinatorially, if you want to compute the dimension of a Schubert variety, you just look at the length of your permutation, or in other words, the number of adjacent transpositions. And something that will appear later as we're comparing Schubert varieties and Hessenberg varieties, codimension ones will be like what we will look at most. So let me give you a characterization using this idea that a Schubert variety has codimension 1 if and only if your permutation is of this form. So it's an adjacent transposition, so it just swaps two adjacent numbers times the longest permutation. It's listing the numbers in opposite order. And just to connect it to something we said before, so yesterday we heard about Cash and Lustig varieties and matrix Schubert varieties, and so those are related to Schubert varieties very strongly. So this I'm okay. So maybe from what I told you, it's unclear why this is a variety, especially if you think as varieties as zero sets of ideals. But if you want to know what equations you can use to define Schubert varieties, then one way you can think about that is using matrix Schubert varieties. Although, yeah, maybe the precise statement would be like the matrices whose cosets lie in Schubert varieties are satisfies conditions given by matrix Schubert varieties. And then the other ones that we learned were about Cash and Lustig varieties. And then just to remind you, those give you like, these are projective varieties, so you can cover them by affine patches, and those patches are going to be centered at torus fixed points, and the equations at each of those patches are given by Cash and Lustig ideals. Okay. Now, here, let me go ahead and start talking about Hessenberg varieties. And yeah, so for this part of the talk, I will change the definition towards the end, but for this part of the talk, I'm gonna start with the Lie algebra of the special linear group. So it's just n by n matrices with trace 0. And we're gonna have the adjoint action or the adjoint representation on this G. So my group G acts on SLNC by conjugation. So now, before defining Hessenberg varieties, let me tell you what a Hessenberg space is. So a Hessenberg space is, so first, this is a vector subspace of n by n matrices with complex entries. So a Hessenberg space is a vector subspace of this G that is B invariant under this action. And so using this, we can define a Hessenberg variety by, so what is the data for that? You start with a Hessenberg space and a matrix in SLN, and you obtain a Hessenberg variety as follows. So it consists of the cosets such that this holds. Okay, so MXM is in H. And there's a little, it's not a hard exercise, but of course, is this well defined? Since I picked a representative, yes, it is well defined. So this is, you can think about, so this is the description of the Hessenberg variety that you can do using the G mod B description. And there's a quick observation. So when you want to construct examples, it's good to start with examples that kind of, well, this is not the most interesting example, but at least helps a little in understanding what's going on. Okay, so what if you have that X is a matrix with all 0 entries? Well, when you conjugate it, you still end up with the same matrix, and this is a subspace, so that better be inside. So when you have that X is this boring matrix, you recover your flag variety. And similarly, if H is everything, well, this is always true. So again, you recover the flag variety. But so now this description, I have nothing against this description, but it takes a little, it's a bit more abstract than, like, it would be nice to have a flag description in the sense of like which flags lie in it. And okay, so you can say, okay, this gives you a flag description because each coset gives you a flag, but can you be more direct, just as we were with Schubert varieties? And under some instances, you can be more direct. So for that, let me denote by B the algebra of the Borel. So these are the upper triangular matrices in SLN or in MathFacT. And I'll define here something that Laura mentioned yesterday, which is a Hessenberg function. So a Hessenberg function is a function from n to n that satisfies that is non-decreasing and that satisfies this property for all I. And so in this case, you have that Hessenberg functions are in one-to-one correspondence with Hessenberg spaces that contain this B. And the bijection, okay, one could write it very not a lot of detail, but it's very easy to see pictorially. So this is an example of a Hessenberg function. And so the way the Hessenberg space corresponding to this Hessenberg function is like, okay, so this 2 tells you these 2 rows don't have to be 0, but then the bottom 3 have to be 0. Then this 4 tells you that, okay, so here you have some freedom, but here you do need to have a 0. This 4 tells you, again, here you have freedom. This should be a 0. This 4 also tells you this should be a 0. And then, well, the 5 doesn't tell you much. Okay, so matrices of this form that have trace equal to 0 are all like, they give you a Hessenberg space. And this is how you can correspond Hessenberg functions to Hessenberg spaces. And in the picture that we had yesterday, Laura was telling us about dig paths, and you can get to dig paths. I mean, she had it rotated, but yeah, I have it written down like this because of my conventions, but this, so all of these are objects that are very much related to each other. Okay, so assuming that you have this condition, and let's suppose that this Hessenberg function corresponds to this Hessenberg space, then in this case, you have that your Hessenberg variety consists of the flags such that for all I, the image under X, so X is a matrix, it's a linear transformation, the image under X of VI is contained in V of HI. Okay, and so this is a different description that, yeah, I find it easier to construct examples from this one. But the downside is you do need this condition. So we can do an example. And our example is going to be, well, let's suppose we have this Hessenberg function. So this Hessenberg function is almost constant. It's h of 1 is n minus 1, and if I is bigger than 1, it's just n. And in that case, well, you want that for all I, x of vi should be contained in v of h of I. And well, most of the cases, this is just c to the n. So this condition is for free. So the only condition that is interesting is this one, where you have x of v1 should be containing vn minus 1. And in this case, you can have the following description. So, and here, yeah, I'm just being sloppy in the sense that I don't want to write h, the Hessenberg space associated to little h. So I'm just going to write Hes of little h. So this Hessenberg variety is going to be the set of flags. So here I'm looking at the matrix. So it's the set of flags v1 containing v1, v2, and so on and so forth, such that the determinant of this matrix is 0. Okay. Because you want this. Okay, so v1 is spanned by v1, and you want this object to be in here, and that's equivalent to forcing this determinant to be 0. And so this is an example of a codimension 1 Hessenberg variety with a very concrete description. Now, originally, these varieties were defined under this assumption that I have here. And they were introduced by the Mary Shaman and the Mary Purchase Shaman. And they discovered some beautiful combinatorial properties for them. So they considered this one, this Hessenberg function, which is, in terms of dict paths, it's like the one that is closest to the diagonal. And so if you start with this Hessenberg function and you pick a diagonal matrix with n distinct diagonal entries, then your Hessenberg variety becomes the toric variety of the braid arrangement. So in other words, the toric variety of the permutation. And this is true, so I'm only telling you about Hessenberg varieties in type A, but this type of relation holds if you went to other types, doing the appropriate, changing the objects appropriate. Now, for all such x, so let me consider now general Hessenberg functions, but fixing x to be a diagonal matrix with n distinct diagonal entries, you have that your Hessenberg variety is always smooth, and its Euler characteristic is n factorial. Okay, so for some, so this is a nice family of Hessenberg varieties. But so yeah, but for the purposes of which Schubert varieties are Hessenberg varieties, this type of ideas start telling you that probably it's good to not assume this to be the case, because then your geometry and your topology is going to be somewhat limited. Okay. Schubert varieties for sure have more complicated Euler characteristics than this. So unless stated, we are not assuming this to be the case. So, and there will be some instances when that happens in our theory, but you should just assume that is not the case. I just introduced it because they do lead to a nice flag description. And I will just give one remark that it's not the center of this talk, but it's important to mention it, is that, yeah, as Laura said before, yesterday, there are interesting questions relating cohomology of Hessenberg varieties to the Stanley-Stanbridge conjecture. And those Hessenberg varieties that appear, they do assume this. So you do have this beautiful flag description. And if you're interested to know more, there's you can talk to any of my colleagues, but in particular, John Shoreshian gave a really nice talk in FIPSAC, and those talks are on their YouTube channel now, so you can look at it. Now, one thing is, okay, so there's nice properties about Hessenberg varieties. For example, they have affine pavings, which let you understand their Poincare polynomial, for example, but there's lots of questions we don't know. So as remember, Schubert varieties are irreducible, but that is not the case in general for Hessenberg varieties. For Schubert varieties, there is a beautiful criterion by Lakshmi and Zambia about which Schubert varieties are smooth. That is not known for Hessenberg varieties. So formulas to compute dimension, that could also be very useful. Lots of questions about the geometry of Hessenberg varieties that we do not understand. And it's kind of why we were interested in our question, because lots is known about Schubert varieties, less is known about Hessenberg. Can we answer this question, and what can we discover in doing so? So let's go ahead and answer this question, or partially answer this question. Which Schubert varieties are equal to a Hessenberg variety? Okay. And it was a bit surprising for us, but pattern avoidance came to play a role in the answer we gave. So we will say that a permutation avoids 4, 2, 3, 1 if there do not exist a sequence of 4 numbers in ascending order, such that if you look at the permutation at those indices, they satisfy this relation. So in other words, this is the same to say as there does not exist a subsequence of your permutation that has the same relative order as 4, 2, 3, 1. And so an example, I don't know about computers, but personally by hand, I find it hard to know if a permutation avoids another permutation. So my example is always, this one is very easy. This is always decreasing, so there's no subsequence is going to have this relative order. because it will always, every subsequence of length 4 is going to have the pattern 4, 3, 2, 1. So this permutation avoids 4, 2, 3, 1. Whereas this one does not avoid it because it contains this subsequence 7, 3, 5, 1. And this has the same relative order as 4, 2, 3, 1. Okay. And so, oh yeah, and of course, I'm just doing it in this case sense because of the theorem, but you can define pattern avoidance for any permutation. So our theorem says that if you start with a permutation in Sn, and here I want to highlight that it's the same n throughout. So if there exists a matrix, and, oh, I forgot and, or maybe I deleted it, I don't know, and a Hessenberg space H such that your Schubert variety is equal to your Hessenberg variety, then your permutation needs to avoid 4, 2, 3, 1. Okay. Now here, when you have pattern avoidance, those are nice results because there are tools, classical tools that let you quantify how many Schubert variety, or how many Schubert varieties can be Hessenberg varieties, or how many permutations avoid a certain pattern. So we have an immediate corollary from the Marcus-Stardust theorem, also known as the Stanley-Wilf conjecture, that most Schubert varieties are not Hessenberg varieties. So namely, this limit, you take the limit of all permutations for which the associated Schubert variety is equal to a Hessenberg variety divided by the number of permutations, this limit goes to 0. Oh yeah, sorry, praise. I just saw your question. Yeah, no, it's not a Lie algebra. Okay, so now a question is, could this be an if and only if, or can pattern avoidance really characterize Schubert varieties that are Hessenberg varieties? And the answer is, well, let's see. So for n equals 4, we computed exactly all the x and h that give us a Schubert varieties, and we have that this holds if and only if W is not any of these 4 permutations. And so with that, we see, okay, so clearly this is not, our theorem is not an if and only if, right? Because we have other permutations that avoid this, but they're not Hessenberg varieties. And on the other hand, this second remark tells us that pattern avoidance is not going to characterize which Schubert varieties are Hessenberg varieties because, well, this, we just said a Schubert variety associated to this permutation is not a Hessenberg variety, but if we put a 5 at the end, it is. And so this permutation contains this pattern, and so pattern avoidance is not going to characterize which Schubert varieties are Hessenberg varieties. Now, I would say that's not too surprising. I find it more surprising the fact that some pattern, we could use patterns to get rid of some Schubert varieties that are not Hessenberg varieties. Now, the other remark I want to say, in case for those of you who know this criterion, so there is this beautiful result that I mentioned before by Lakshmi and Zambia, who say that a Schubert variety is smooth if and only if its permutation avoids 2 patterns. One of this is one of the patterns, and the other one is 3, 4, 1, 2. So this is getting rid of half of the non-smooth Schubert varieties, but the other pattern can appear as a Hessenberg variety. Oh, and then a last remark that I want to make, I'll leave this here, is that, okay, so we also have a type C version of our theorem, which, okay, so when you have pattern avoidance exists in other types. And in my opinion, the easiest one is type C because your type C wild group, you can realize it as a subgroup of the type A wild group. So in particular, this is a type C permutation, and you can define pattern, or one way you can define pattern avoidance in type C is just the one that's inherited from type A. And so we also proved this result in type C. Okay, so there's type C Schubert varieties, type C Hessenberg varieties, and this theorem holds if you just replace everything for type C. And a key tool that we use to prove this, like one of our key lemmas that I find it's an interesting result on its own, is this idea. So if you're familiar with type C, one of the things, or the way I think about type C is you start with type A, you have an involution on your type A flag variety, and you looked at the fixed points. And if you look at the fixed points, you get the type C Schubert, type C flag variety. You look at the type C fixed points of a Schubert variety, you get a type C Schubert variety. And we prove the analogous statement, which is that if you start with a type A Hessenberg variety and you look at the sigma fixed points, you obtain a type C Schubert variety, and every type C Schubert variety appears in this way. So this is new, and it leads to the possibility of translating some of what we know in type A into type C world. Gives us an extra. Okay, so now, so that question of equality, it's nice, and it lets us lead it gave us pattern avoidance. But the more interesting question is which Schubert varieties are isomorphic, because then they share more geometric properties. You know, this tells us how different the two families of varieties are, in my opinion. But this question is very, very general. For one to be able to approach this question, you really need to understand a lot about the geometry of Hessenberg varieties, which is not, as I said before, some things are known, but other things are not. And so rather than answering this very broad question, I'm going to concentrate on the codimension 1 case. Okay, so which codimension 1 Schubert varieties are isomorphic to a codimension 1 Hessenberg variety? And of course, like if you're going to show that two varieties are isomorphic, you can try to give an isomorphism. But if you want to show that they're not isomorphic, well, you probably want to use invariants. So here are the invariants that are most important to us. So if you have two varieties that are isomorphic, well, they better both be irreducible or both not be irreducible. So if we want to answer this question, given that Schubert varieties are irreducible, we want to restrict to irreducible Hessenberg varieties. Now, another invariant is, okay, if you have two isomorphic varieties, their Euler characteristic and their Poincare polynomial should agree. And now here, this is actually quite useful in the sense that I keep on saying there's not that many tools and things like that, but when it comes to Euler characteristic and Poincare polynomials, both families, Schubert and Hessenberg varieties, have a lot of tools. So Hessenberg varieties have affine pavings, and Juliana Timochko proved this for type A, Martha Prekop for general type, and not only, and they use their affine pavings to give methods to compute Euler characteristics and Poincare polynomials. Now, the third one is, okay, so if you have two isomorphic varieties, well, their singular loci should be isomorphic as varieties. And here for Schubert varieties, the singular locus of a Schubert variety has been studied, lots of tools. Now, that is not the case for Hessenberg varieties. So we're gonna look at, well, these are going to be the two most important tools, but in doing so, we will have to discuss the singular locus of a codimension 1 Hessenberg variety. Okay, so using these invariants, we were able to prove the following theorem. So suppose we have a permutation that gives us a codimension 1 Schubert variety. And I'll emphasize again, this is important. So I mean codimension 1 in the same flag. So the n should be the same. I'm not that like if I wanted to be like, I don't know, find a that's a really difficult question. Like if you give me a Schubert variety in flags sub 7, can you find a Hessenberg variety in flags sub 100 that is somehow isomorphic to your Schubert variety? That is really hard. So instead, we're gonna fix the n is going to be the same for all of them. So let's suppose we have a permutation that gives us like this form, so that this is a codimension 1 Schubert variety. So there exists a Hessenberg variety in the same flag isomorphic to this codimension 1 Schubert variety, if and only if I is 1 or n. So there's only, so those are the only cases in which your Schubert variety can be isomorphic to a codimension 1 Hessenberg variety. And so to prove this theorem, we had to use different tools. And so, but the first one is we need to characterize codimension 1 Hessenberg varieties. And so here, this is our characterization. So if you have a codimension 1 Hessenberg variety, then there's only two possibilities. Either your X has an eigenspace of dimension n-1, or H has to be this Hessenberg space. Okay, so this so you can have anything you want here, but this should be 0, which is the Hessenberg space associated to the Hessenberg function that I gave the example a while ago. It was the example that we did. So to start it, and moreover, if your Hessenberg variety is also irreducible, then the Euler characteristic of that of this codimension 1 Hessenberg variety is divisible by n-2 factorial. So here we have the opportunity to use the Euler characteristic of Schubert varieties to try to compare the two Euler characteristics. So on the one, like if we, and this is not hard, this is quite known that the Euler characteristic of a Schubert variety, you can just, I mean, it's just the Bruhat decomposition, right? It's the number of cells in the Bruhat decomposition of your Schubert variety. And so it's the set of permutations that are less than or equal than SIW0 under the Bruhat order. And one can count that and not to that exercise to see that this is equal to n factorial minus I factorial times n minus I factorial. So here, the only possibility, the only way this can be isomorphic to a codimension 1 is, well, they both have to be irreducible, or this one has to be irreducible because this one is, and this number has to be divisible by n-2 factorial. And so just comparing the numbers, that is like the only way this divides this number. It's the complement. Okay, so let me just read it because I'm doing complements. So if I is none of these 4 numbers and n comma I is none of these 2 pairs, then you cannot find, then there is no irreducible Hessenberg variety of codimension 1 such that this is true. Okay, so that's a consequence from when can this number divide that. And so to prove our theorem, we just need to, well, that gets rid of, that almost proves our theorem in all our cases. We just need to show that for these 2 numbers, I don't know why I wrote them in that order, but for these 2 numbers, they are Hessenberg varieties. The associated Schubert varieties are Hessenberg varieties. And then for all the other ones, they're not. So this case, we have that if X, we basically utilize this lemma that if X has an eigenspace of dimension n-1, and this Hessenberg variety is irreducible of codimension 1, then this is going to be true. One of these two holds. But in fact, we can actually realize it as equality. So Juliana Timochko had some work on Hessenberg varieties that of highest weight, but I won't get too much into it. But using her work, one can show that these two are equal to some Hessenberg variety that Juliana studied. Okay, so this case is not too bad. Now the case I equals 2 comma n minus 2, well, that one that here is where we use the singular locus of each of the varieties. Okay. So we were able to give a characterization of the singular locus of some Hessenberg varieties of codimension 1. So if this Hessenberg variety is of codimension 1 with X nilpotent, and so it being codimension 1 and X being nilpotent forces H to be this Hessenberg space, then the singular locus of your original Hessenberg variety is equal to, it's a Hessenberg variety on itself, okay, with the same X, but your H changes. So rather than having this H, your H prime becomes this. And this to us was surprising, not only to be able to compute the singular locus, but also that it gives you a Hessenberg variety again. Now, and in the case of Schubert varieties, the singular locus of a Schubert variety is a union of Schubert varieties, and that it's one of the reasons it's nice to, like, one can study it and compute it, and everything you know about a Schubert variety of the family of Schubert varieties becomes things you know about the family of singular loci of Schubert varieties. But that is not the case for Hessenberg. So this to us is very interesting. And so in particular here, well, once we're able to say that the singular locus of this Hessenberg is a Hessenberg itself, we can compute its Euler characteristic. So if your Hessenberg variety has codimension 1 and the same Betti numbers as any of these two Schubert varieties, and they have the same Betti numbers, so it has the same Betti numbers as both these two Schubert varieties, then this is the case. So there are Hessenberg varieties that have the same Betti numbers as this Schubert variety. So that's why our previous strategy of, well, like, we got rid of lots of examples using Betti numbers, but it didn't work out for this family or for this Schubert variety, this family of Schubert varieties. But then, okay, so they have the same Betti numbers, but then when we look at the singular locus, their Euler characteristics are not going to be the same. Okay. And one thing I want to just say, because I know some people here think about those, is that so a tool to prove this theorem and to understand the singular locus very well, were the patch ideals that we heard about, that Emmanuel was telling us about yesterday. His were for Schubert varieties, but one can describe the definition for subvarieties of the flat variety. This is by work by Insko and Young, or, well, partially, well, it appears in a paper by Insko and Young. And using those patch ideals, you can study the singular locus of Hessenberg varieties. And this has been done by numerous people, and in particular, it's what allowed us to come up with this equation. And okay, so then the last case that we have is, it was this weird case where n was 8 and I was either 3 or 5, but that was kind of an accident, in the sense that maybe we just got rid of lots of families using a given criterion, but if we had used a different one, you would have seen that this is not the case. But in any case, this is just settled case by case using formulas from Betti numbers from work by Martha Prikop. Now, I wanna, okay, so far I've been doing things in type A, And for this, okay, so we saw maybe two families of Hessenberg varieties, one more general than the other. One was when the Borel was contained in your Hessenberg space. And then the other one is you just have a Hessenberg space with that, without that condition. But now I'm gonna go maybe to the opposite end and go to as much generality as possible for Hessenberg varieties. Okay, so Goreski, Kotwitz, and McPherson, they extended the definition of a Hessenberg variety. And the way they did it is, okay, so we're gonna need something else. They're gonna vary a representation. So there was a representation hidden in my previous definition. So we're gonna let G be a connected reductive group, and we're gonna take a finite dimensional rational representation. And so with that, now our Hessenberg spaces are going to be subspaces of this vector space B that are being invariant under our representation. Okay. So now here, if you let H be a Hessenberg space in this generality and B be an element of our vector space, our new very general definition of a Hessenberg variety, and this is not standard, but I'm just putting there so we can compare. This Hessenberg variety is the set of cosets such that this holds. Okay. Okay. So why is this more general, where it includes our previous definition? How does it include our previous definition? Well, you recover what we had before if you let psi be the adjoint representation. So what is the adjoint representation for non-experts? In that case, B is the Lie algebra, and the representation acts as follows. So this really does recover what we had before. So our theorem in this case is, okay, so let me show you. So if we start with a strictly dominant weight for G, and for if we think about type A, we can make lambda be this n minus 1 all the way up to 1. Then the dominant weights, forget about this strictly for a second, the dominant weights of G are in one-to-one correspondence with irreducible representations of G. Okay. So in particular, this lambda is going to have a representation associated to it. But strictly dominant leads us for it to be a highest weight representation. And here, we're gonna let V sub lambda be the highest weight vector for this representation. So in this setting, you have that for every Schubert variety, there exists a Hessenberg space H sub W inside here, such that this equality holds. Then it's not like I don't need to worry about isomorphism at this point. They're just equal. So every Schubert variety is a Hessenberg variety from this level of generality. And it's, I do find it a bit surprising that you don't even need to vary the V. It's with the same V. Now, what is this? What is this H sub W? So this is something that is very classical from representation theory. This is called the Masur module. And so here, basically, it's a module, a B module generated by some element. I mean, you just act on this V by W inverse, and you have the module V module generated by that, and like classical literature, in particular, a result by Bernstein, Gelfand, tells us, it kind of gives us this theorem. It almost gives us this theorem, which says that it gives you a translation saying that, okay, so it basically tells you that the torus fixed points of the Schubert variety are going to be in here, or sorry, or let me say it in a different way. The torus fixed points on the flat variety are going to be in here if and only if they satisfy Bruchard order. That will follow from classical results from the demonstrator module by Bernstein, Gelfand. And so because we were looking at torus fixed points, and there's a torus action acting on this, that basically leads us to these two varieties being equal. But I will give a little disclaimer that this family of varieties, of Hessenberg varieties, is very general. There's few things that are known about them. It's like, we know some things, but in terms of like what geometric properties do they satisfy, what geometric properties do they not satisfy, not much is known. They're very, very general. And so in particular, like there are other families of varieties that are known to be this general Hessenberg varieties. So work by Oblomkov and Yoon, they have shown that many interesting curves and surfaces are Hessenberg varieties of this generality. So in some sense, I'm curious, like what sort of varieties cannot be Hessenberg varieties of this level of generality. I would like to know. But yeah, that is all that I have for you. So thank you so much for your attention.
Okay, let's thank Laura for a very nice talk. And are there questions?